we have been talking about hidden surface elimination methods, right? So last time we were talking of a method based on area subdivision. So the idea was that you take an area which is to be displayed, a region of the screen, and then you determine the visibility for that area, right? And you try to figure out whether one of the simple cases gets satisfied within that area of interest, right? So we looked at 4 cases where a polygon could be a surrounding polygon to the area, it could be an intersecting polygon to the area, it could be contained in that area, or it could be disjoint to the area, right? So we try to classify the relationship of the polygon with respect to the area and then decide, right, what to do. And if the case is not a simple case, then we subdivide it further, right? So everything happens in an image space, right? So the area is a displayable area which is in the image space. So the computation happens in image space. So now today we are going to look at another approach which is also of the kind area subdivision, right? But instead of subdividing the area which is to be displayed, we would subdivide the polygon. Okay. So what do I mean by that? So that's the area subdivision where the area was subdivided into 4 parts was the technique suggested by Warnock's method. So there is another technique by Weiler-Atherton where the subdivision takes place along the polygon boundaries, right? So what do I mean by that? If you have, let us say, these polygons to be displayed, right, where one of the polygon obscures part of the other polygon, then what we are trying to say here is that the subdivision is in terms of the boundary of the polygon where this polygon obscures this, right. So in some sense it is a clipping method, right. So we are trying to discard or consider a piece of the polygon, right. So this is the subdivision which has now taken place for this polygon where you get this part and this part along the boundary of this polygon, right. So now after these 2 fragments of the pieces which have been obtained, you figure out whether to display that fragment or not, right, depending on the depth of the polygon. So the subdivision or the fragmentation is along the boundary of the polygon, right. So here the precision where you are doing the subdivision is of object space, right. Okay. So now what we are saying for the algorithm here is that we first do an initial sort in Z or depth, right. Consider the frontmost polygon, clip all polygons to generate pieces or fragments inside polygon and outside polygon. So there is a list for inside polygon and there is a list for outside polygon against the polygon you have considered for clipping, right. And this polygon you have picked on the basis of your initial Z sort, the basis of which could be anything, right. So if you find out that all the inside polygons are behind this clipping polygon, right, then you delete those polygons from the list to display, right, because the polygon pieces which you have gathered turned out to be behind this polygon against which you are clipping, then you need not worry about those polygons, right. So you just discard them. However, there could be instances where there is an inside polygon in front of this clipping polygon. So, that is an offending polygon, because we had considered an initial z sort on some basis which may not hold true in the real scenario, right, because this could be based on, let us say, maximum z of the polygon, and that may get violated by some of the polygon to decide whether it is in front or behind. So, if you do find an offending or offending polygons, then all you have to do is consider that to be the clip polygon and do this process again, right. So, clip the inside list of polygons against this polygon, okay, and then you process the outside polygons, right. So, broadly what we are saying, there is a notion of building an inside list and there is a notion of building an outside list, right. So, first you process the inside list, just determining the visibility of the polygons within that list, right, and if it turns out that the inside list is all obscured and occluded by this clipping polygon, then you just delete them, discard them, and consider the outside polygon list, and so on, right. So, just to illustrate through an example, consider a very simple scenario where you have, let us say, a polygon A here and this is polygon B, right. So, and let us say this is the z axis and where you are determining the depth of these polygons. So, this is x, y, z, and you are viewing somewhere there from this end, right. So, this is in front of that, as you see in this situation. So, what are we saying here is that the initial sort when is taken, A turns out to be the first polygon to be picked, right, as the clipping polygon. So, you consider A as clip polygon, you build the inside list where you have this clip polygon A itself, right, and then there is a portion of B which is inside A, right. So, that is the portion which you would find inside A, right, which is in the inside list, right, and then you have the outside list which is this part of the polygon of B, which is B out A. So, I am just labeling them as B in A, the portion of the polygon B which is inside A when you perform clipping, and B out A is the portion of the polygon B which is outside A. It is just a labeling. Right. Now, when you look at the relative visibility between A and B in A, which is the content of the inside list, you find out that A is in front of B in A, right, or B in A is behind A, therefore, you just delete that, you do not have to worry about this. So, therefore, you just display A, right, and then you process the outside list polygon which is B out A, and here it turns out to be a trivial case because this is the only polygon left. So, therefore, you display B out A. Okay. So, the whole method relies on, in some sense, subdividing these polygons into pieces or fragments, right, and establish the visibility of these fragments with respect to a polygon which you consider in front, and keep doing that, right. So, take another example. Let us say there is an example here where you have a polygon A here, there is another polygon B here. So, when you look at in this view, right, so this is A and this is B, right. So, in Z when you see it, this is A polygon and this is B polygon. Okay. Now, when we do this building of inside list and outside list, what you will observe is the following, that so you first of all consider A as the clip polygon, because A is, if you look at the Z max of A, is the greatest, right, is the largest value. Therefore, you consider A to be the clip polygon, right, just on the basis of your initial Z sort, right. So, you consider A as the clip polygon. So, you build the inside list which contains the clip polygon itself first, A, and then the portion of the polygon B which is inside A, which is B in A, right, and then the contents of the outside list just has B out A, the remaining portion of the polygon B, right. Now, what happens when you look at the visibility of B in A with respect to A? It turns out that B in A is not behind A, is actually in front of A, right. So, I cannot discard that. Therefore, I choose B and A now as the clip polygon. See, as opposed to the other scenario where I had B and A behind A, and I could easily delete the fragment B and A from the list and display A. Here I cannot, because this turns out to be in front of A, right. So, I pick this as now the clip polygon, right, and then the inside list is B and A itself and A in B, right. That is the portion of A in B. In fact, while I am performing the clipping, though strictly speaking I am referring to the clipping against the piece or the fragment B in A, but for the purpose of performing clipping of A, I could perform the clipping with respect to B itself to determine A and B, right. So, I do not need to perform this clipping against the fragment, right. So, this is the inside list. Now, the outside list is the B out A, which was already there, and A out B with respect to B and A. Fine. So, now I figure out that B and A, now A in B is behind B and A, again I establish through the visibility test, right. So, therefore, I display B and A, and then I continue this process, right. So, this is how the Euler-Atherton algorithm works, right. So, these were sort of simple scenario. You may encounter scenarios like this, right. There are more number of polygons, therefore, there are more fragmentation, more fragments here, right. So, all it boils down to is to determine these fragments, right, which may look like this, and then look at the relative visibility of these fragments, right. So, at the end you will have some display of the fragments. So, there will be an order of display of these fragments. Right. So, maybe you should consider an example of this nature and work out yourself to understand the whole algorithm. Fine. Okay, so now we move on to another hidden surface elimination method. Well, it would very much depend on the amount of the fragmentation that can happen, right?
But let's say we have say n fragments, then can we establish conservation?
So, yeah, then what we are saying is that the maximum or let's say the worst case could be that given a polygon here, let's say I'm trying to establish this is a polygon A, right, and all the polygons render or give me the fragments to be tested, then I'm basically testing with respect to each of those fragments, and this can happen for all the polygons, right? So it could be n square. Right. Now there is a situation, for instance, when we're talking about, let's say, this case, right. So what we observe is that this polygon which is in front of this, so there is no penetration or interpenetration of polygons, right. Things are a little hard when, let's say, if this polygon goes and comes beyond this, then you may actually do the split of the polygon in 3D, right, and then do this process.
So their fragmentation won't help?
No, because what will happen is, see, this would not be, if you look at this will be somewhere there and there will be a line here, right. So this line would not appear in the projection, right. So what do I mean here? Let's see. See, what I am saying is that, let's say, this may actually extend up to this, right, and this line is not there. What you need is to get this line, right, and that you would get it through the split of the polygon, right.
So, but still the top edge of this extended polygon which is behind A,
Right.
that you will get by projection.
Yeah, see, this is okay, this is fine, this is not the issue. The issue is that what would you get for B? So how would you determine the pieces as B in A and B in out A? See, there is an ambiguity there, unless you have this line, right. Okay, so now let's try to see another method of hidden surface elimination, which is actually a combination of, in some sense, Z buffer and scanline conversion of polygons, right. So it's a scanline algorithm basically, and it is based on scanline coherence across multiple scan lines or span coherence. So what do we mean by this is that what happens is, when you scan convert a polygon, then you get span or portion of the scan line within different polygons, right. For a given scan line, you will have spans of this scan line contained in different polygons. So all you are trying to do is take those spans and figure out which polygons these spans belong to, right. And if they just belong to one, then the visibility is determined. So just color with the polygon it comes from, right. So it is sort of embedded in the process of scan conversion of the polygon, right. So let me sort of elaborate on it. So, what do we mean by here? So, first of all, we are referring these spans. What do we mean by spans? These are nothing but portion of the scan line. So, if this is a scan line here, there is a span here. This is also a span, but outside the polygons, and this is also a span inside another polygon, right. So, these pieces of scan line inside or outside the polygons are the spans.
So these polygons are projections, or
these are projections. Okay. So, again you have span here, span here, span here, and so on, right. So, ultimately when it comes to figuring out the visibility, then we are looking at the visibility for this span, visibility for this span, and visibility for that span, and appropriately decide how to render these spans. Right. Okay. So, what we are saying here is, just to give you an overview of this method, each scan line is subdivided into these several spans. You determine which polygon the current span it belongs to, right. Shade or color the span using the current polygon's color or shade, right. So, in a sense, what we are doing, we are actually exploiting the coherence within this span, right, because once we have established that this span is contained in a particular polygon, and this is the polygon which is to be displayed, right, all the pixels or all the points along that span could directly be rendered, right. So, we are exploiting in some sense this span coherence, and for each span, as we observed, a visibility test may be required to be performed, right, particularly when there are more than one polygons which are intercepted by a span, right. So, as I was saying, that you may have different kinds of spans, right. There is a span which is inside only one polygon, right. This is the span, this is a polygon A, this is a polygon B. For this particular scan line, this span is contained in one polygon, right. There is another span which is also inside span. So, there is a span of the kind inside span and outside span, right. So, inside span are those which are contained in some polygon, and then you have these outside spans which are not inside any of the polygons, right. So, a different strategy may be required depending on whether the inside span is within one polygon or more than one polygon, right. Okay. So, now just to give you how do we determine this inside outside spans, right. So, again as I said, the scan line is divided into a sequence of spans, and it may be an inside span or outside span, right. So, the outside span is that no pixel need to be drawn, or you draw the background color, right, because it is not contained in any of the polygons. The inside span, it can be either inside one polygon or more than one polygon, right. So, if a span is inside one polygon, the pixels in the span will be drawn with the color of that polygon, fairly simple, right. And if a span is inside more than one polygon, then you need to resolve for the visibility, and which may be through the z value of the polygons, right. So, the question comes, if we are talking about this labeling of inside outside spans or inside one polygon inside multiple polygons, how do we do that? No, visibility test would be required in terms of resolving for z values, right, where we have figured out that this particular span is contained in multiple polygons, right. Now, let us say just labeling inside span and outside span, how would you find this out? Intersection with polygon edges. So, but again intersection would not really give you inside outside. See, intersections would just, pardon me?
If you had to parity check.
Yeah, you need to have some sort of a parity check to be able to decide which span is inside, which span is outside, right. So, it is very much similar to what we have seen in the scan conversion, right. Okay, so that is what is more or less said here, that when a scan line intersects an edge of a polygon, for the first time the span becomes inside of the polygon, right, from that intersection point onwards. For a second time the span becomes outside of the polygon from that point onwards. So, this is what the parity test is, right. So, you just count the number of edges it intersects of the polygon and then decide whether it is getting in or getting out. Right, and then you sort of put a flag in or out for each polygon, right, to track the current state, right. So, initially you may label all these polygons, let us say, to be outside, and then do this check.
But there may be intersecting polygons and then two vectors such intersects maybe inside.
Okay, so you are referring to some complicated case, so we will come to that. It is piercing, right, it is a penetrated polygon.
Yeah, two polygons which have like simply some overlapping region.
No, overlapping region is not a problem, that is not a problem, that we will be able to handle it. See, right now we are just labeling the inside outside.
Still, but we are saying that we mark the alternate intersection points.
No, see, we are putting the polygon inside. So, we are labeling a polygon, right. For this particular scan line, what are the inside polygons, right, and the track of that would actually determine for a particular span whether this span is contained in this polygon or more than two polygons and so on. So, I will give you an example and that will illustrate it better. Okay. So, what we are saying is that each polygon has got now its own flag, which is saying whether it is an in flag or out flag, right. And they could be now more than one polygon having the flags as in, right. So, all we are saying is that we just have to keep track of polygons, right, where the scan line is currently in. Okay. And if there are more than one polygon in, then we need to perform this z value thing, right. resolving the visibility for those polygons. Right. Okay. So, now as far as the data structure is concerned, so that was sort of the sketch of the algorithm we had. So, for implementing this, you may have a data structure which contains, let us say, an edge table and a polygon table. Right. So, edge table has got the value of x, right, for the lowest y, right, the value of x for the lowest y, and then you have the y max, right, for the edge. You have the increment of delta x, right, which could be in fact the inverse of the slope, right, to tells you what increment you give to get to the next point, and the ID of the polygon which the edge is contained in, right. So, it is a identification of the polygon and so on. So, these are the fields in the edge table. For the polygon table, you have the ID of the polygon, the definition of the polygon or the plane of which the polygon is made. So, these are the coefficients of Ax plus By plus Cz plus D. So, the definition of the plane of the polygon, the color or the shade it has, right, and the flag in and out. So, that will be maintained. Fine. So, in addition to this, we may have some sort of an auxiliary data structure, which is in some sense an active in Polygon list, right, which is just an indication of what are the polygons which are marked in, right. And similarly, there is an active edge table.
Why do you need the inode flag? Just add the polygon to this list if it's inside.
Yeah, so it's actually either you process that polygon table, right, or you just have an auxiliary data structure which contains this in Polygon list, right. So, it may not require an explicit storage, right. So, it may just be an operation. Okay. Right. So, this active edge table contains the edges of the polygon which are under process for a particular scan line. Okay. Let me give you an example now. So, let us say this is the scenario. BG stands for background, right. There is a polygon S, there is another polygon T, and let us say you artificially define some extent of the range of the scan line, right. So, these could be sort of vertical edges like x naught and x n. Right. We just give you the finite limited view of the display area, right. So, and these are, let us say, the scan lines we are interested in 1, 2, 3, 4. Okay. So, if you look at now the various scan lines here, so you have the active edge table for this particular scan line, where all it contains are these edges, right. You have the in Polygon list, which is giving you the polygons which are intercepted by this scan line, right. So, further detail on it. So, let us say if I am talking about scan line number 1, right. So, with respect to the active edge table, what do I have? X naught, right. So, this is the vertical edge where located at x naught. The edge B A, right, this edge of the polygon, the edge B C there, and x n, right. So, this is the content of the active edge table for this scanline. Similarly, for in Polygon list, I have BG, right. Then I have BG plus S, right, which is this polygon on the top of the background. Then I have again background, right. So, now looking at this, it is sort of easy to process what action you need to do, right. So, you just wherever you find BG active, you display the BG. Now, there is only one polygon on the top of BG, therefore, you display that polygon, and then again BG. It is straightforward. Similarly, if I let us say go for this scan line, I have x naught, B A, B C, and again now this edge 3 2, 3 1 and x n, right. As far as the polygons are concerned, background plus S here, again background plus T here, and again background. So, this is again a simple case where I have the overlap of the polygons on the top of the background, which are disjoint, right. So, as far as the processing of this is concerned, it is straightforward, right. Similarly, if I go to now number 3, things are a little different now. So, I have x naught, B A, 3 2, A C or C A, 1 3 and x n, right. As far as the in Polygon list is concerned, this is background plus S. Now, I have background plus S plus T, right. So, there is a span which is contained in more than one polygon, right. Then again I have background plus T and background, right. So, this is where I need to do something extra now, where I have more than one polygon flagged as in, right. So, I would resolve it with respect to Z to decide which of the polygon needs to be rendered, right. So, again for fourth it is a simple case, right. So, you see the two data structures we refer to, the edge, the active edge table and the in Polygon list, how they basically give you the sequence of rendering you need, right. Once you look at this, you know what to do, right. Okay. Now, there could be some.
But how do we construct those data structures?
How do we construct those data structures? Tell me.
Consider case 3, sir.
Consider case 3.
For example, IPL, how will we know that?
So, what are we saying? We are saying that for a given scan line, what are the polygons which get flagged as in, right. And we also have, so what do we have here? This is the background and this S comes, right. Now, it intersects this, right. So, what do you get? another in polygon, right. So, you have not exit from polygon S.
Because we haven't exited from polygon.
Pardon me?
Yeah, because we haven't exited from polygon S and we have encountered another in polygon.
Right. So you basically doing the intersection of the scan line with various edges of the polygon and then doing this parity thing, right. So, S would exit here when you intersect from this edge, right. That is where the parity test gives you that yes, you are out.
Parity is captured in this data set.
Parity is captured in this, right. So, it is just a matter of finding the intersection of the edges and then labeling appropriately the polygons to be in. Fine. Okay. So, the next thing what I was saying is that you can actually exploit certain. So, let us say there is a scenario where there is a big polygon, or this could also be considered as the background of the scene, where you have polygon A and polygon B, and what we consider here is that these polygons are non-penetrating. That means, they are not penetrating with each other, right. So, there is a distinct gap between the Z values, right. So, in that case there could be some advantages when you are doing the rendering with respect to a scan line. So, let us say if we are talking about this scan line here, right. So, when I encounter the polygon A, right. So, this becomes in some sense the obscuring polygon for C, right. So, I keep rendering it here and now I encounter another polygon B, which is obscuring A and also C, right. Here what happens is that I exit the obscured polygon A, right. So, let us say we are only considering between A and B and C to be some background thing, right. So, here I exit the obscured polygon A, right. So, now what could be done is that, so here in fact I do not need to perform the Z check. So, if I am flagging this that yes, this is an obscured polygon, right, then further on I do not have to worry about what happens to the Z values. Right. So, this is just to make this process more efficient. Any further suggestion which you can use here for, let us say, accelerating the process? In the case of non-penetrating situation.
So we shouldn't find the intersection.
We shouldn't find the intersection. What do we do?
The upper polygon, we find the intersection for the upper polygon, then we should discard the lower polygon all the way. We don't need to even find the intersection, next intersection.
No, we need to find out the intersection with the edges, because otherwise we don't know what spans are there, right. That is required. Now, try to see what happens if there is a scan line just above it here, and from that scan line you have come here. What is the information you can carry? In fact, the scan line above this was exactly same in terms of the in polygon list, right. So, there is a sense of depth coherence from one scan line to another scan line, unless you hit points like this or point like this, right, where the AAT, the active edge list changes, right, then there's something else to be done. But if AAT is the same, then there is a coherence between one scan line to another scan line for the depth. So, once you have performed the visibility for a scan line for which the AAT is the same, you need not perform the visibility for the next scan line. Is it clear? Right. So, there is this depth coherence we have between scan lines. Now, what happens if I have a situation where things are not so simple? Instead of having a non-penetrating situation, I have a penetrating situation. So, what do I do? Can you visualize the penetrating situation? There could be this A, let us say, coming out of B, right? That is a penetrating situation.
This is the line of intersection of the polygons.
Yeah.
To be projected.
So, something similar to what we were saying in the case of Lec-30. So, there is a notion of some false edge to be given, right, which indicates this penetration, right. So, what we are saying is something like this. We have a polygon S, and this is the part which comes out of T, right. So, that is where it is penetrating. So, what you need is definition of this edge, right, and in some sense this to be a sort of an extra polygon. Maybe it is referring to the same polygon as this for the color information, but for treating the other labeling of IPL, you need another additional polygon here, right. So, what we are doing is we are adding these, let us say, false edge and false polygon. Right. So, if you look at with respect to this scan line here, this is what you have is the AAT, which is the active edge list, where you have this edge EC, and this is your polygon list in IPL, where you have the polygon as BG plus S plus T plus something, whatever that is. Right. So, with this you can handle now the penetrating polygons, right. So, more or less this covers, I think, the hidden surface elimination, whatever I plan to do. Next time we will do something else. Have you heard about fractals? Yes, fractals. What have you heard about?
Certain functions, so start applying f of x, f of x, f of x is known.
Right.
We iteratively plot those using a geometric pattern on screen.
Okay. Okay. So, any application you know?
They help in generation of natural scenes.
They help in generating natural scenes. So, see, there is a nice property they have, which is called as the self similarity. So, if you try to zoom in, you see a similar structure as to where it had started from, right. So, we are going to look at how these fractals could be useful in the context of modeling, right. So, one application could be the natural phenomena, modeling natural phenomena, right. And you might have also seen the fractals used as a function, where Mandelbrot set, if you have heard about it. So, that is also a factor. Right. So, we are going to talk about that. Thank you.